Okay, let's work some NMR problems. So in this video, I'm going to work through the NMR problems on the practice exam on eCampus. If you're in my Summer 1 2020 class and you previously downloaded the practice exam, go back and grab it again. I replaced it so that there's not a bunch of chapter 16 on it. But okay, anyway, we will jump in. We're going to look at problem 13 first. Now, on problem 13, you'll notice that the next page walks you through a bunch of steps to solve for the answer here. I'm going to answer these questions, but I'm going to stay on this page. Okay, so I come to an integrated problem like this, meaning I've got IR and carbon NMR and proton NMR. So I have a lot of things to work with. I also have a chemical formula. So hopefully by now you know what I'm going to do first. I'm going to find those degrees of unsaturation. So I see 10 carbons. So it's going to be 2 times 10 plus 2 minus 12 hydrogen. Leave the oxygen alone, divide by 2. So what does that give me? I have 22 minus 12. Oh, my Lord. Okay, 10 divided by 2. We have 5 degrees of unsaturation. So this is my inventory at the top. 10 carbon, 12 hydrogen, 2 oxygen, 5 degrees of unsaturation. All right, now I am going to go to the IR first. Let's see what we can see. I got a big old blob. So what does that tell me? Carboxylic acid. All right, I've got my C double bond O here as well. So I've got 2 oxygen. This IR told me exactly what I needed to know about those oxygen. I've got a carboxylic acid. That's one of my degrees of unsaturation, 1 carbon, 2 oxygens, and a hydrogen. Now, to find out what the other 9 carbon and 11 hydrogen are doing, I'm going to need to go into the NMR. You can't really tell if there's sp2 and sp3CHs. A lot of times if you have sp3CHs, they'll peek out down here, but I wouldn't rule them out. Carboxylic acids make everything else in this region a little hard to read. So from the IR, I know I have a carboxylic acid. Now, with carbon NMR, so I'm just going to reference this here. You can probably solve this whole problem without using the carbon, but the carbon will help you double check what you made. Or if you just are less intimidated by it, you could certainly start there. I can see, for instance, 1, 2, 3, 4, 5, 6, 7, 8 types of carbon. So if I have 8 types of carbon, but 10 carbon overall, then I know at least a couple of my carbons are in the same chemical environment. I also can tell that my carbonyl is down here, right, well above 150. I've got 4 types of carbon in the aromatic space, and then 3 carbons down below 40, so more of your kind of like alkane piece. So definitely some information you can start with right there. You could also use it just at the end. So if I go to the proton NMR, and this is the most complicated region, but it's where I'm going to get a lot of information, I'm going to start breaking things down. Now, hopefully this is clear enough for you to see the pattern. On your exam, if it's not super clear, it will be labeled. So for instance, this is a doublet and this is a doublet, so I would label that. This right here is a triplet, as is this. I think you can see those, but just in case you can't. You will notice something here that maybe you didn't notice in the really pretty NMRs from the lecture. Sometimes your signals lean, right? So the triplet isn't perfectly 1 to 2 to 1. One side's a little bit taller than the other. That's actually pretty common. A lot of times signals will lean a little bit like this, and it's nothing to be alarmed about. Here, I would say this one's a little bit trickier. You could initially look at it and want to call it a sextet, but anything above a quartet, a lot of times I leave or call a multiplet until I have more information, right? Because you can start to see whatever little peaks out here start to get lost. Can't forget this. I also have one hydrogen down here. No real pattern helping me, but it is almost to 12. And that's that carboxylic acid proton, right? Okay, now, next, let's think about the integrations. 2, 4, 6, 8, 9, 10, 11. So there's not a lot of symmetry in this molecule. You see all of your hydrogens represented, right? It's not like there are only 5 or 6 integrated. So you're seeing all of the hydrogens here. Now, something that I always gravitate to early is this 7 to 8 region. You notice they cut everything out between 3 and 7. That's because there's nothing there. So if you see portions cut out, that's why. It's not tricking you. It's not hiding from you. It's flat. There's nothing there. 7 to 8 is a big deal. This is aromatic, right? So I know that I am going to have a piece like this. If I have an aromatic ring, that's all of my degrees of unsaturation, right? I have 1 for the carbonyl, and then 2, 3, 4 for the double bonds in the ring, and then 5 for the ring itself. So that's all my degrees of unsaturation. I also know that that's where 6 of my carbons are, and then I have a 7th carbon here, and so I only have 3 carbons left. So I'm starting to take down from my inventory. I also know that 4 hydrogens are on this ring. So it is a di-substituted benzene ring. I know that I have 4 aromatic protons. And if you listen to my lecture, this is actually a really, really nice, pretty example of a 1-4 substitution pattern. So there's something here and there's something here. If it was 1-2 or 1-3, this region would still integrate to 4 hydrogens, but it would be messy. Because it is 1-4, you have a degree of symmetry. This hydrogen and this hydrogen are going to be identical. This hydrogen and this hydrogen are going to be identical. And they're going to split each other into doublets. So I know a couple of big pieces now. So what's next? Let me go to the sort of aliphatic, the alkane region of the proton NMR. This messiness down here. Now, if I have 3 identical hydrogens right here, the most likely way that 3 hydrogens are in the same chemical environment is if you have a methyl group, right? Otherwise, there would have to be just some insane symmetry, and we just don't have enough carbon and hydrogen left over for that. It's split into a triplet, so this is a CH2 with 2 neighbors. All right, so it's a CH3 that's next to a CH2. So I'm going to leave that alone for just a second, and I'm going to look at the other 2 signals I've yet to mess with. This one here is a little bit more complicated, so let's look at the triplet. If I have 2 identical hydrogen, easiest scenario is that it's a CH2. But this CH2 also has 2 neighbors, right? So it is a triplet, so it's got 2 neighbors. So this CH2 is not connected to the CH3. It would at least be a quartet, right? So I know that from just looking at these 2 triplets. Now, if I go to this final 2 hydrogen, again, most likely scenario, it's a CH2 of some sort. It's not a triplet. It's not a quartet. So it can't just be attached to a CH2 or a CH3. It's not likely that it is attached to something with, five identical hydrogen, but it could very well just be a multiplet, and it is being split by both a CH2 and a CH3. This often happens when you have a carbon chain. The CH2s in the middle tend to be a little bit muddy. They're a little bit more messy or kind of clumped together like you see here. And that's because the CH2 on the left and the CH3 on the right are splitting it. And they're not wildly different J values, but they are different. And so it gives you a more complex piece. All right, so from this, and it goes nicely here, right? You have 3 alkane carbons. So the most likely scenario here is that we have a CH2, CH2, CH3. So now, if I go to my inventory, I know where all my degrees of unsaturation are. I know where my oxygens are. I have 6 carbons from the benzene ring, 7, 8, 9 from this propyl group, and then 10 from the carboxylic acid. I've got 1 hydrogen and then 4 aromatics, so 5 hydrogen, 6, 7, 8, 9, 10, 11, 12. So this accounts for everything in the inventory, all of the atoms, all of the degrees of unsaturation, and now it's my job to put them together. In this case, it's actually pretty darn easy. I essentially have a puzzle that has 2 end pieces and 1 middle piece, right? If I put them all here so I can look at them next to each other, if I were to put the carboxylic acid and the propyl together, there would be no place for the benzene ring to go, right? So the benzene ring has 2 places that need attachments. And so what's going to make the most sense is for that to go in the middle. So whenever I draw my final product, I'm going to put the carboxylic acid on one side, and I'm going to put the propyl group, goodness, the propyl group on the other side. And that is how I solved this problem. Now, if I want to use the carbon NMR to double check myself, right, I've got my carboxylic acid, I've got my propyl group, and then I've got 4 signals in the aromatic region, but I have 6 aromatic carbons. Well, that makes sense. This carbon and this carbon are identical. This carbon and this carbon are also identical. So most likely those 2 real big tall peaks are representing those. However, you can't really tell with concentration, so I would just say, well, there are 4 types of carbon in that ring. There are 4 types of aromatic carbons. Here, this structure matches with this carbon NMR. So I hope that helps you start to break down this type of problem. I'm going to continue on. I'm going to work some of the other NMR problems in this exam. For instance, I want to work a problem where you only have NMR and show you that that's also possible. Well, it's not even true here. You still have some IR information. Let's look at one where it seems like we have a lot less info. C4H9Br. So how many degrees of unsaturation are there? 2 times 4 plus 2 minus 9 minus 1 for the bromine divided by 2. So that's going to be 8, 9, 10 minus 9 minus 1. Okay, so there's no degrees of unsaturation. That's great. No double bonds, no rings. We have IR peaks at 2966 and 2937. So the IR is letting us know that there's sp3CHs. Super helpful. So it is helpful because it actually tells us there's no other functional groups to worry about. So if you didn't get the degrees of unsaturation right here, this is basically telling you that as well. There's no hydrogens on double bonds. There's no hydrogens on triple bonds. There's no carbonyls, although honestly, there's no oxygen, so that should also be obvious. So let's go in here and look. Now, again, this wasn't super clear, so you can see we have labels. We have two doublets and we have a multiplet. So if we have two hydrogen that are identical, CH2 is most likely. And if it's a doublet, that means it has one neighbor, right? That is going to be what splits it into a doublet. Our one hydrogen is a multiplet. And so there's one type of hydrogen. That means, we have a CH in there somewhere, and it's being split in a way that is more complicated. So it could be attached to that CH2, but it's also got some other things going on. Then we have 6 identical hydrogen. Now, how are you going to get 6 identical hydrogen? Well, we only have 4 carbons, so it can't be 6 super symmetrical CHs. 3 symmetrical CH2s is going to be pretty unlikely, especially given that we already know we have a CH2 and a CH, so we that can't happen. But it is a multiple of 3. So what is most likely is that we have 2 identical CH3s with one neighbor. Now, the most likely way that methyl groups are going to be identical is, again, either with an extreme amount of symmetry or if they're on the same carbon. Now, since we only have 4 carbon, that's going to be the easiest way here. So this is where we're at with our NMR. We have a CH2 being split by one carbon or one hydrogen, a CH, and then 2 identical CH3s. What you also need to remember is that you also have a bromine. So we have 3 end pieces. So I would say don't put the bromine on a methyl group. That will end the story. And then let's think about how we could put this together to get the splitting that we're seeing. Now, the CH3s shouldn't go onto the CH2 because then this would be a triplet instead of a doublet. It really only makes sense if they're on the CH. So I have a CH, and if both CH3s are attached to it, then they would be in identical chemical environments. Then, again, if I put the bromine next, I'll be out of luck with the CH2. And also the CH2 needs one neighbor, so that's going to come next. And then we're going to put the bromine out here. This also makes sense with the CH2 being out above 3, that bromine is shifting it downfield. And that is how I would solve for number 14. I also wanted, so there will be a solution for problem 15 up on eCampus, but I wanted to solve a problem where you don't have the pictures to look at, because this is another way you might be presented with NMR data. So I've got IR and NMR data here. I've also got carbon NMR. So I'm going to start off, you guessed it, degrees of unsaturation. 2 times 8 plus 2 minus 9, skip oxygen, minus 1 for the chlorine, divided by 2. So I've got 16, 17, 18, minus 9 is 9, minus 1 is 8. Okay, 4 degrees of unsaturation. My IR tells me I have a broad peak from 36 to 3400. It's a little bit high, but that's going to be an OH. I usually expect to see them centered around 3300, but in this region, the OH is the most likely culprit there. I've got 1, 2, 3, 4, 5, 6 types of carbon, so at least a couple of carbons are in the same chemical environment. So you don't have to do this, but I'm going to sketch out my NMR as I'm talking through it. So at 7.5, I have a doublet that integrates to 2 hydrogen. At 7.1, I have a doublet that integrates to 2 hydrogen. The J values are given, and that helps you to know what is splitting what. Remember, that's telling you about the space here. So most likely, these two signals are coupled together. They're splitting each other. Then at 3.7, I have a triplet, and it represents 2 hydrogen. At 3.0, I have a singlet that represents 1 hydrogen. The height that I'm drawing doesn't have to do with anything. At 2.7, I have a triplet that represents 2 hydrogen. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. All of my hydrogen are accounted for here. Now, what you should know at this point, I'm going to tell you. I have 2 doublets in the aromatic region. I have 4 aromatic hydrogen. This is wonderful news. This tells me a huge part of my compound. And since it's 2 doublets, it's not messy. It is going to be 1,4 substitution, just like in the first problem we did. All right, now what's left? I still have 2 carbon. I still have 5 hydrogen. Well, we know one of them's an OH, so I still have 4, 5. I still have 4 hydrogen. And let's see what's going on. I've got a CH2 with 2 neighbors because it's a triplet. I've got 1 hydrogen, no neighbors, or at least nothing splitting it. This is most likely my OH. It's a singlet. And then I've got another CH2 with 2 neighbors. So if I have 2 CH2s, and they both have 2 neighbors, well, what's the most likely scenario? I have a CH2, CH2. That means there's no neighbors on this side, no neighbors on this side, because they're both pretty triplets. So let's see, what do I know? I have this little CH2, CH2. I have an OH. I have a Cl. And what else do I have? Oh, and I have a benzene ring. Is this everything I need? Well, this is my 4 degrees of unsaturation, right? 3 double bonds in a ring. I've got my O, I've got my Cl, I've got 6, 7, 8 carbons. I have 4 hydrogen on my ring, 5 on the alcohol, 6, 7, 8, 9. So everything is present and accounted for. So how can I put it together? Let's see. I know that okay, there's actually 2 ways you could put this together, and I would give you full credit if you were taking this particular test. Now, you have 2 middle pieces. So if you put an OH and a Cl either on both sides of the CH2, CH2 or the ring, then you will have left a piece out. So I know that the CH2, CH2 and the ring need to go together so that nothing gets left out. Now, whether the OH is directly on the ring or the Cl is, it's not necessarily obvious, right? You're going to have a chemical shift here for both of those CH2s because on one side there's a ring and on the other side there's an electronegative element. Whether you put the chlorine or the O there, it would shift it down. So I would accept this answer. I would also accept, in this case, the oxygen and the chlorine being switched. If you could get to either of these answers, then you have done your job. All right. I hope this helped. I hope seeing me work through a few problems was helpful. If you would like more of these videos, let me know if there's a certain problem that you would like to see me work out and we can't meet together in office hours, I'd be happy to make another video. Just stay in touch.